So this is shear, example 4, continued, page 5. So in this case here, we're going to be considering the stresses in the web. The stresses in the weld. So there's a neat little picture which shows probably these bits isolated, and then along here, and in fact in all four corners, if there wasn't a weld, then obviously the bits would be separated. So if there was a weld, then there would be a force in terms of kilonewtons per millimeter that needs to be resisted, and that's the force that the weld needs to resist. So we're asked to calculate that value. Let's do this in terms of the shear stress. So the first thing then is to calculate the shear stress at the position of the welds. And the position of the welds, if we'll just deal with one of the welds, since all four of the welds are the same. So that's relative to the position of the neutral axis. And we know from before that the distance to the weld was going to be 280 millimeters. So it's a distance up or down of 280 millimeters. So we go back to our equation. Tau as a function of y is going to be equal to v times s dash as a function of y, and that needs to be I times b as a function of y. So we want now to work out our value tau at 280 millimeters, and that's going to be the shear stress at the weld, and that's going to be equal to v times s dash of 280 millimeters divided by I, which is the second moment of inertia about the neutral axis, times b as a function of y, which is also 280 millimeters. So we know that our I from before is going to be 1.361 times 10 to the 9 millimeters to the fourth. We know that our V is going to be 1750 kilonewtons. The breadth at 280 millimeters upwards, that is again going to be our combined breadth, since we're trying to work out our stresses. So that's going to be 2 times 12 millimeters, which is going to be equal to 24 millimeters. So the only thing as before to work out is this S dash at 280 millimeters. So let's try and calculate that. So we have we have our section. So that's badly sketched. And we know that that's going to be the neutral axis, and this time we want to do a cut here. And if we work out the value of S dash at the cut, that's going to be that's going to be the value of S dash that we need to put in. So we could take that bit out. We still have the neutral axis here, and then we could calculate our S dash at 280 millimeters. Alternatively, the other way to do it is to neutral axis and then draw the two webs going down here. Because our cut is going to be there, and then S dash again of 280 millimeters is the first moment of area about the neutral axis of everything that's been shown. The first, they should both give the same answer, of course. Whether you do that calculation or whether you do that calculation, you should get exactly the same answer, but I think it's obvious that the first calculation is a bit easier. So the S dash there is going to be the area of the top flange, so that's going to be area 1, area A1, which we've already calculated, and that value is 6 times 10 to the 3 millimeters squared, and that needs to be multiplied by the distance of the centroid of that bit to the neutral axis. So the centroid is there, and the dimension, the distance of that line is going to be 300 minus 10, which is going to be 290 millimeters. So times 290 millimeters being the distance of the centroid, so put those bit in brackets, 290 millimeters, and that is going to work out to be 1.74 times 10 to the 6 millimeters cubed. So that's going to lead us to that value there of 1.74 times 10 to the 6 millimeters cubed. And so if we then worked out the whole expression for the stress in the weld, that's going to be that's going to calculate out to be 93.233 newtons per millimeter squared. So, recalling our shape, if we plotted the shear stress in the web at the neutral axis, so it's going to go something like there, and then the horizontal part, and then out to there, and then it's going to go back down again. So that's going to be the shear. So what we've done so far is to calculate the value of the stress. So the value of the stress at that point so that value has now been calculated to be 93.23 newtons per millimeter squared. And remember that in our other calculation we calculated the Tmax to be 143.644 newtons per millimeter squared. So if we now wanted to turn that value that we have calculated into a traction, so there's shear stress acting up here. So there are shear stresses acting here, and if we wanted to turn those shear stresses into a force. Sorry for talking so slowly. I'm not sure it's recording. I'll just give it a minute to catch up. Okay, so we have the shears. They're going to be acting some shear stresses along up here. If that is a blown out portion of that there, which would obviously be the shear stress acting on the web as well. So to calculate those shear stresses, we would need to multiply that value by the thickness of the section. So we could then say demand on each weld is going to be equal to tau at 280 millimeters multiplied by the thickness of each web. So that's going to be multiplied by 12 millimeters, since that's going to be the thickness of each web, and that is going to work out to be 1.19 kilonewtons per millimeter, which means that each weld, each of the 4 welds therefore needs to carry 1.19 kilonewtons per millimeter, and the distance in the millimeters is acting in that direction. So it's sort of providing a shear stress along the length of the web as it runs along the length of the beam. It's easier to say in that direction 1.19 kilonewtons per millimeter, or 93.233 newtons per millimeter squared, which is the same value, except that the 1.19 is the result of the 93.23 being multiplied by the thickness of the web.